If we can categorize a molecule into a point group, we can use this symmetry to simplify the process of describing vibrational modes. Let's look at water as an example. Water is defined by the C2V point group, and the C2V character table is shown. As a brief reminder, the character table shows the name of the point group, all of the symmetry operations that belong to this point group. In this case, E is the identity operator, which does nothing. C2 is a rotation operator, which rotates the molecule about an axis of 180 degrees. And two mirror operators, which reflect the molecule in the plane, in this case the XZ plane and the YZ plane. The value h here is the order of the group, and we can calculate this easily by summing up the numbers before the symmetry operations, 1 plus 1 plus 1 plus 1. In the left-hand column we have a symmetry species. These are irreducible representations which are described by A, B, etc. Finally, the table itself has characters, the number 1 meaning symmetric and -1 meaning antisymmetric. The right-hand columns list the functions. These are important as the first column of functions contain the x, y, z and relate to infrared activity. The second column lists quadratic functions and relate to Raman activity, as we'll see later. The process involves the determination of a reducible representation that describes the vectors of movement of each of the atoms in the molecule, where the movement includes translational, rotational and vibrational. Once we have done this, we will remove the translational and rotational movements, thus use the remaining information to arrive at the vibrational modes of the molecule. As mentioned, water has C2V symmetry. The first step is to define the x, y and z axes as shown. The second step is to describe the reducible representation for all possible movements of the atoms in water. When we complete an operation contained in the character table, if the vector remains unchanged, we assign it a value of 1. If the vector moves, we assign it a value of 0. And if the vector is reversed, we assign it a value of -1. Let's take each one in turn. The identity operator leaves the molecule unchanged. Therefore each atom remains unchanged, and the 3 vectors on each atom remain unchanged. 3 atoms, each with 3 vectors, mean there are 9 unchanged vectors, so a value of +9 is entered into our reducible representation. For C2 rotation, the hydrogen atoms switch positions, while the oxygen rotates in the same position. What happens to each vector? For hydrogen, the vectors have completely moved, so each of the 6 vectors returns a value of 0. For oxygen, let's take each axis in turn. Rotating the molecule does not change the z-axis, so it returns a value of +1. For the x and y axis, the vector rotates 180 degrees to the opposite direction, so they each return a value of -1. Thus the overall total is +1, -1, -1, giving us a total of -1. For the mirror reflection of the xz plane, the molecule is bisected. Again, the hydrogens exchange, so their vectors return a value of 0 as they have moved. The x and z axis for the oxygen are in the mirror plane, so they remain unchanged, returning a value of +1 each. And the y-axis of oxygen is reflected in the plane, so its direction changes 180 degrees and is assigned a value of -1, giving an overall total of +1. Finally, the mirror plane in the YZ plane, which is the plane of the computer screen, the atoms stay in the same position, and only the x-axis vectors of each of the 3 atoms change direction by 180 degrees. Hence, we have a value of +6 -3 is equal to +3. Therefore, the reducible representation represents all of the modes of movement for the water molecule. We now need to see what combination of irreducible representations give rise to this reducible representation. This can occasionally be done by eye, but it's easiest to use a simple formulaic approach, which effectively factors out the number of each of the irreducible representations contained in this reducible representation. We can say that the number n of each irreducible representation can be obtained by multiplying the character of the irreducible representation by the character in the reducible representation by the number in front of the class, all divided by the order of the group H. This sounds more complex than it really is. Let's take one example. For A1, the number is 9 times 1 times 1 for E, plus minus 1 times 1 times 1 for C2, plus 1 times 1 times 1 for the first mirror operator, and 3 times 1 times 1 for the second. All of this summed up gives us 12 divided by 4, which is a value of 3. So there are 3 A1 irreducible representations contained in this reducible representation. We can repeat this for each one, and I suggest you pause the video here and try them yourself. And when you press play, you can compare your answers with mine. You'll see here that we now have 1 A2, 2 B1, and 3 B2 irreducible representations joining our 3 A1 that we worked out in full. Therefore, the total number of modes of movement is given by these. But we're only interested in vibrational modes, so we can remove the translational and rotational movements. So, we will remove a mode for B1 for the X, a B2 for the Y, and an A1 for the Z. We subtract for the rotational, a B2, a B1, and an A2 for the 3 rotational movements, or X, or Y, and or Z. Note here that if there were 2 translational or rotational movements for a particular irreducible representation, we would only subtract it once. So for example, if X and Y are in the same line, we would only subtract that once. Once these are subtracted, we are left with the vibrational motions, and we can see that we have 3 modes as expected, 2 A1 and a B2. Finally, we can check which of these are infrared active. If they have an X, Y, or Z next to it in the function column, it is IR active, as it involves a displacement and hence a change in dipole moment. In the case of A1, it has a Z value, and therefore it is infrared active. In the case of B2, it has a Y value, and therefore it is infrared active. Indeed, both of these also have quadratic functions associated with them in the final column of the character table, so they are also Raman active. What are these modes? Well, we know from symmetry that the B2 is antisymmetric with respect to the principal rotation axis, and from the spectrum we would see that it occurs at 3756 wave numbers. The first A1 is a symmetric stretch at 3657, and the second is a bend which is also symmetric, and this appears at 1595 in the spectrum. One final thing to note when you're applying it to other molecules. In this case, when we looked at change in vectors, where the vector had changed by 180 degrees. There are some scenarios where the vector changes but by a smaller amount, e.g. 120 degrees due to a C3 rotation. The actual value we assign is more correctly the cosine of the angle, alpha. Therefore, for a C3 rotation where the vector rotates by 120 degrees, cosine of 120 is minus 0.5, so that will be the value we assigned. You can see for the 2 scenarios we've already considered, where the vector remains unchanged and the vector reverses direction, you can see where we get these values. For a value of 180 degrees, cosine of 180 gives us minus 1, as used before. A value of 360 degrees, in other words the vector doesn't change direction, results in cosine of 360, which is plus 1, as used before.